means something. All right, let's get started here. First things first, I'll open the door. Second things, we've got our quiz. I guess I should write that here. Uh, 16. Quiz 4 is a week out. What? We just had a quiz. I know, you're telling me. But it's our last quiz. And then it's final exam time. Eek. The reason I wanted to do a quiz 4 just after these few chapters is because there's still a lot of material in there, right? Hypothesis testing, confidence intervals. And last week we started, we did chapter 16, one sample proportions, right? Confidence intervals, hypothesis testing for one sample proportions. Today we're gonna do 2 sample proportions. And then on Thursday, we build it up to 2 categorical variables in a table, right? So comparing 2 categorical variables and their categories, allowing for as many categories as we need. And so this is on Tuesday. Eek. Oh, that doesn't look, that looks like a mean smiley face. I wanted to do a, it's not a smiley face. So, because it was tempting to do, 16, 17, 18, 19, 20, 21, all on one quiz, but that's too much. We want to have it nice and condensed, I guess. There's still a lot. Yeah. And then we can really sort out kind of the kinks before the final exam. Okay? And so, of course, the emphasis will be on numerical data analysis for the final exam, right? But it is cumulative, so we'll see all of the quiz stuff. Maybe not so much quiz 1. We didn't really, we're kind of built on that all term, right? But 2, 3, 4, all important. Okay, so been nearly a week. So any questions before I get started? I feel like there was something. No. Happy St. Patrick's Day yesterday for those who celebrate. Inference, an umbrella term for hypothesis testing and confidence intervals, right? Hypothesis testing and confidence intervals. What's nice is 2 sample proportions is going to be very similar to 1 sample proportion, right? So last week we had a sample proportion, so some proportion of successes, and we wanted to compare them to some number. And don't worry, I put ChatGPT on the case, so we have a better example. In fact, I was like, oh, what the heck, let's use 2. I've not tried them, so we'll see how they go. We need to lay some rules out for 2 sample proportions, because what's going to happen now? If I have 2 samples, right, or 2 groups, we can think of them as, right? Right, so 2 samples or 2 groups. Or 2 groups, right? 1 sample from each group. What does that mean? It means I have 2 sample sizes, All right. And is this one? Maybe I'll do I'll make it green for St. Patrick's Day. Oh, change the ample or amp, whatever. Two groups means that I'm going to have an N1. So usually we denote them with a subscript 1 and an N2. Right. Maybe I'll separate these like that. I have two sample sizes now. I'm going to have either some number of successes in group 1 and some number of successes in group 2, which I can then use, or I've been given the proportions, right? I'm going to have a P1 hat and a P2 hat. Clean up that hat. If you only look at one of the groups, that's the same information that we had for one sample proportion. It's just that now I have two samples, and so it makes sense that I'm going to have information from both. Okay? Our ultimate goal is to compare these two sample proportions, right? And we want to know, are these two sample proportions significantly different from each other, right? So now I'm not comparing it to a number anymore, right? Before I just had one sample proportion and I wanted to compare it to some number, right? Now I have two sample proportions and I want to compare them to each other. Okay? And so here, we want to compare the proportions to each other. Let's tackle the hypothesis testing steps first, right? What do you need to know? You need to know the null hypothesis, right? And you need to know, well, how do I calculate the test statistic? Okay. And then after that, you're all set. I know it doesn't feel like that yet, but eventually you'll get to a point where you will feel all set and you can just do this hypothesis test. Okay. And so for a hypothesis testing, right, we want to compare, are these two groups significantly different from each other? And so your null hypothesis, or step 1, is to state the hypotheses. It says hypotheses. You're going to have a null hypothesis and an alternative hypothesis, just like before. Right. Now your null hypothesis, you've done work, right? Figuring out, okay, well, what is my null hypothesis? Your null hypothesis is one where you have to assume that there's no change or that these two groups are the same, right? And so you have to assume that they're the same until you have proof otherwise. Okay? And so what we want to hypothesize is about P1 minus P2. Those are the population proportions. If they're the same, what's P1 minus P2? 1 minus 1 is 0. 2 minus 2 is still 0. So we hypothesize that this difference is 0. Or if you prefer, you're welcome to use either one, but you only have to pick one. Okay? There's a reason that I'm doing this kind of arguably more complicated one. Okay. But what if you added P2 to both sides? Right. Then your null hypothesis would be that P1 equals P2. Right. The reason I say that this one is kind of simpler in a way is because we want to compare these proportions to each other. So it's easier to think about, okay, P1 and P2. However, the reason I do this one first is because that's going to represent our point estimate, right? P1 hat minus P2 hat is our best guess at what P1 minus P2 looks like. Okay, and so that's why I do it this way. But if you prefer to write it this way, you're welcome to. I know what you mean, right? I know what both of them are. Just pick one that you like, okay? And then be consistent with your alternative hypothesis. Okay. So P1 minus P2, let's say, is not equal to 0, right? That difference is not 0. I don't care which direction. That makes it a two-sided test, right? Which means I want the area in both the tails for my p-value. I'll clean that up. Okay. P1 minus P2, if you want to show that one is less than the other, right, that's going to affect the sign in your alternative hypothesis, right? And I think it's a little bit harder to think about how this difference relates to 0, okay? And so I usually just kind of encourage you to use the second one, but I want you to see the symmetry. P1 not equal to P2, but here it's easier to say P1 is less than P2 or P1 is greater than P2, but as a default, use not equal to, right? In fact, if you're doing any sort of publications and things like that, proper analyses, you should probably use a two-sided test. Why? Because it makes it harder to make a type 1 error, right? Rejecting H naught when you shouldn't. Okay? And so just in general, we should always just use a two-sided test, but we have some practice with one-sided tests, right? As P1 less than P2, right? If I want to know, just as a side note here, if P1 is less than P2, right, then P1 minus P2, right? You can move it over if you want, but P1 minus P2, if P1 is less than P2, you would get a negative number, right? Less than 0. Okay, so that you have to do a little bit more kind of work, I think, in this scenario. Wait, erase there. So that's our null hypothesis, right? We want to compare these two things. Okay. And yeah, let's do it. Step 2 of a hypothesis test, I call it do the test because it sounds cooler, but it's really calculate the test statistic. Do the test, do the do. But I guess we don't watch commercials anymore. You don't know do the do. Mountain Dew commercials. Yeah. Do the test. Okay. Now, you'll be relieved to know that in the end, we get a Z. Why is that a relief? Because we know how Z behaves. We know how to find areas under the curve with Zs, right? And so, okay, that's light at the end of the tunnel, right? Because then once I have my Z calculated, right, it's going to be a little bit bigger because I have to incorporate all this information, right, one way or another. Okay. And so it's going to be a little bit bigger, but once I have my Z, then for my p-value, I find it the exact same way that we've been doing, right, for the one sample proportions and before. Right? So with the normal distribution, norm.s.dist gives you the area under the curve, and then you're off to the races. Okay. So what does, well, as a little bit of review, I guess, let's do this. Your test statistic in general is your point estimate minus the null value divided by the standard error of the point estimate. That's in general. For us, our test statistic is a Z, and don't worry, on Thursday, we see a brand new test statistic. Very exciting, the chi-squared. I can't believe it. So soon? You think we're ready? I know you're ready. Z is our test statistic in this case. Your point estimate is your best guess at whatever it is you're hypothesizing about, right? I'd say my best guess at what P1 minus P2 looks like is P1 hat minus P2 hat. Right? I take my information that I've got from my sample, and that's my point estimate. So P1 hat minus P2 hat, that's my best guess at P1 minus P2. That's my null value. But I've also hypothesized, right? And I have to do all my testing, assuming the null hypothesis is true, right? And so I've also hypothesized that P1 minus P2 is 0, which makes this part go away, right? I just replace it with 0. Okay. And so that's why, or maybe I'll do H naught says that P1 minus P2 is 0. And so I can replace that with 0. And so usually on your formula sheet, I don't even write this, just because I don't want you to kind of get tripped up. I usually only write P1 hat minus P2 hat, right? But the reason is from here, right? And that's a little bit trickier to see if you use this version of the hypotheses. Right. And so that's why I wanted to start here. But if this makes more sense to you, they're the same. Right. And so that's fine. You can use whichever one you want. As long as you don't jump from this H naught to this HA, that would be very weird. Right. To me. Now, the standard error. We have a problem. The standard error in the one sample proportion, we use the null value. Right. We used our null hypothesized value, right? The standard error of P hat, we said was P naught Q naught over N. That's from last week. So we use our null value, but our null value is 0. So that's not going to help us at all. And so instead we say, okay, how about this? If, I'll erase this. If these two proportions are the same, which we're going to assume until we have proof otherwise, shouldn't I be able to toss them all into a pool? And I don't care if it's a success from group 1 or a success from group 2. And my total sample sizes, they can all just go into a pool, right? And it's called the pooled estimate. And so that's why I'm thinking of them as a pool. And I've searched high and low. There's a textbook at one point where there's a graphic of a test statistic, like a Z just tossing successes and failures into a pool, like a kiddie pool. But I can't find it anywhere. Anyways, pretty cute. So you assume that these two proportions are the same. So it shouldn't matter. You should, if they're the same, then they can just all go into one group, and we call that the pooled proportion. Now here is where you need to hang on tight, because our standard error is going to be P hat. What? But we have P1, P2, P1 hat, P2 hat. I know, and now I'm introducing this P hat, where P hat is the pooled proportion. That's going to be different from our P hat from our one sample situation, right? And so you really got to keep your wits about you. How are we going to find p hat? P hat is the total successes divided by the total sample size. And usually I'll write it out in words, and depending on what information you have, right, it could be as simple as x1 plus x2. If I give you the number of successes in each group, then you can just add them all up over n1 plus n2. Right? Or if I only give you the n's and the p hats, then you need to calculate your successes, right? Then you'd have n1, p1 hat plus n2 p2 hat divided by n1 plus n2. So it depends on what information you have. Just as all our q's, q hat is 1 minus p hat, right? Any q is just 1 minus that p, right? Q naught is 1 minus p naught, q hat is 1 minus p hat, right? All the same. And it's just because I'm lazy. So we do p hat, q hat. But you have to find that pooled proportion. Times 1 over n1 plus 1 over n2. And then that's the end of our root. Whoopsies. If you prefer to distribute that p hat, q hat, that's fine, right? Distribute in what way? You could distribute it over n1 and then over n2, but you'd still have to add up those fractions. I find that this is a little bit cleaner to solve for and then multiply by p hat, q hat. So this is the way that I'm going to put it on your formula sheet. And I'll give you the p hat, of course. Okay. A little bit more complicated Z, right? But we can handle it. Right? Once we have a Z, then step 3, use the normal distribution to find your p-value, right? So once you have your Z, then you're off to the races. Step 3, find the p-value, right? Z follows the normal distribution, centered on 0 with a standard deviation of 1, right? Same as before. And I'll save it for our example. And then step 4 is our conclusion, right? Once you have your p-value, you can state your conclusion. And that's going to be the same as always. If the p-value is less than the alpha level, then you have enough evidence to reject H naught in favor of HA. And so, same as before. I know, we were so close to an example.
This is what is Z approximate, but the same as what?
Same as before. Ugh. Huh. How about a confidence interval? So that's our bare bones structure for the hypothesis test. Maybe I'll highlight that here. Then we're able to establish, so after a hypothesis test, we can establish if these two things are significantly different from each other, right? Whereas a confidence interval is a common follow-up, right? Especially if we found that they're different, then we want to know, okay, well, how different, right? What's a reasonable interval for that difference, right? And so for our confidence interval, highlight it to match. is going to, so in general, now I think I used, in general, a confidence interval is our point estimate plus minus our critical value times the standard error of the point estimate. The problem with proportions is we saw it before, right? In the confidence interval for a one sample proportion, we used our p hats, right? Square root of p hat q hat, right, over n. And so it's going to be slightly different for the confidence interval versus the hypothesis test, right? Because now I don't assume that they're the same, right? I just want to know, okay, what's the difference? And so then I can use my p1 hat, pq hat over n, just like you probably wanted to earlier. So our point estimate stays the same though. P1 hat minus P2 hat. I like to throw brackets around there because it's just one difference, right? Plus minus our critical value is still a Z star, right? How many standard errors do I need to move out to create this level of confidence, right? 1.96 for a 95% confidence interval, 1.645, right? 2.578 for a 99. We had to memorize them. Now I don't remember them. Clearly not a good exercise. I'll give you the critical values. For this quiz, I'll say for a 95% confidence interval, use a Z star equal to this, right? So you don't have to read that Excel output. For this stuff, just for your p-values and your, well, just your p-values, I guess. P1 hat, Q1 hat over N1 plus P2 hat, Q2 hat over N2. That looks similar, right? Similar to what we had up here. Oh, I guess I can't really have them on the same. If I had distributed this pooled proportion and the flip side of it, right, that would look very similar. In general, so this is how we build our confidence interval. And then interpreting the confidence interval, we have to remember that we're interpreting the difference in proportions, and that's the only change. Right, and so here, in our interpretation, we need to remember this interval is for the difference in proportions. You can use the confidence interval to see if the difference in proportions is different from 0 words, right? Because if 0 is inside the interval, then that's a perfectly reasonable difference and there's no evidence that they're different from each other, right? But if 0 is outside the interval on either side, right, then that is evidence against H0, right? And so we can use the confidence interval to test the hypothesis as well. Okay. What? There was something. Okay, that's okay. It'll come to me. There was something I wanted to say. Okay, that's okay. just like in the one sample proportion scenario, right? We had to check our conditions. On the quiz, I'll say you may assume that the conditions for inference are satisfied, right? It's more of kind of an assignment thing, or you know, kind of take your time and look it up and make sure you're checking all your conditions. So it's not really a quiz thing. But just like the one sample proportion, the conditions that we check depends on if I'm going to do a confidence interval or a hypothesis test, right? Because of how I calculated my standard error, right? And so the conditions either rely on the pooled estimate if I'm about to do a confidence interval, or they rely on just the sample proportions if I'm going to do a confidence interval. And if a question asks me to do both, I would have to do both. And so, but besides that, and taking into account that I have two groups that I need to check, right? The conditions are the same as the one sample proportion case. And so the conditions slash assumptions we have to check for independence. Right. In general, our conditions were independence and normality, right? And normality we check by the sample size. Okay. Can I assume normality? Oh, haha, I remembered it. I remembered what I was going to say. The central limit theorem says that P1 minus P2 follows a normal distribution centered on 0 with a standard error of the square root of P1 Q1 over N plus P2 Q2 over N2, whoops, N1, N2. I guess technically it's centered on P1 minus P2, but we assume it's 0. You don't need to worry about that, right? But we do need to check our conditions to make sure that we can assume it follows a normal distribution, right? And so that's the reason we have to check our conditions. But this is kind of ignorable theory, right? And it took a lot of practice. So my supervisor, he'd always say, oh, why are you reading that part of the textbook? Because I'm like, oh, I can't see how this part connects to this part. And he's like, oh, that's just theory, just skip that. How am I supposed to know that? Right? And so, so you can ignore that. It's there, and we are relying on it, and we're using it and abusing it. And maybe I should just say, you can ignore this. But in reality, the Z, that's from this, right? But we need to check the conditions. Independence. I have to have independent observations. Now I have two groups, which means I have to have independent observations in each group. Reasonable enough, right? And so our observations must be independent of each other in each group. How can we accomplish that? One way that we feel confident saying that is if we have sampled randomly, right? And so here we can accomplish this by random samples. Right? That's why we we need to collect random samples is because then I can assume that these things are independent of each other, right? I have two groups. I also need to assume that these two groups are independent of each other, right? There's no overlap, right, between the groups. They have to be two distinct groups. And so the two groups must be independent of each other. Right? No overlap. That's relatively easy to do, right? Especially if you're sampling, you know, in West Kelowna and in Vernon, for example, then you have these two independent groups, right? Or we assume that they're independent of each other, right? If they're connected by some, I don't know, water pathway or whatever, then maybe not, but we have to assume that they are. That's your independence condition. The normality condition. So normality, which we sometimes call the sample size condition because it hinges on, the normality hinges on the sample size. Depends on if we're going to do a confidence interval or a hypothesis test. I guess I should do them in the order that I introduced them. So it depends on whether we are doing a hypothesis test or a confidence interval. And if you're about to do both, then you need to check both, right? And it's probably just safe to check both. We'll start with the hypothesis testing. What was our condition for the hypothesis testing? For one sample proportion, right? I had to have at least 10 expected successes and at least 10 expected failures, right, in my sample. So now, same as before, at least 10 expected successes and at least 10, oops, expected failures. Oops. Failures. That was it for one sample proportion, but now I have two groups, and so I need to check it for both groups. And so in both groups, how can I, in both groups, the expectation comes from the null hypothesis, and the null hypothesis is that they're the same, which is represented by our pooled proportion. And so then we use our pooled proportion in checking the expected successes and failures, right? And so I remember it. Now you don't have to memorize it, but how I remember it is whatever I use in my standard error, right? For a hypothesis test, I use the pooled proportion. So that's what I'm going to use to check my conditions. Whereas in a confidence interval, I use the sample proportions. And so that's what I would use to check my conditions. Okay. But like I said, it's more of a an assignment, kind of sit down and think about it and check your conditions thing, not a quiz thing. And so the expected, what color can I use here? The expected, we use p hat, the pooled proportion. And we need to check that n1 times p hat has to be greater than or equal to 10. N 2 times p hat has to be greater than or equal to 10. N1 times q hat has to be greater than or equal to 10, and N2 times q hat has to be greater than or equal to 10. Those are my expected successes and failures for each group, right? N1 and N2, if they are the same, right? If we're doing a confidence interval, and I'm curious to see, can I pull it off on this one page? I need at least 10 observed successes. That's the same as one sample proportion, and at least 10 observed failures, but now in each group. In each group. If you, if you have the successes, you can use those, right? If you have x1, then great. It just has to be greater than or equal to 10, right? And x2, but x1 is the same thing as n1 times p1 hat. Has to be greater than or equal to 10. That's the expected number, or sorry, the observed number of successes in group 1. Let's do it for group 2. x2, which is the same thing as n2 times p2 hat, has to be greater than or equal to 10. Now for my failures, if I have n observations and x successes, then I have n minus x failures, right? And so what you could do is you could check if n1 minus x1, which is the same thing as n1 times q1 hat, is greater than or equal to 10. And then you do the same thing for group 2. My total minus my successes, those are failures, n2 times q2 hat has to be greater than or equal to 10. Now, the pooled proportion. No, I'll close it. Thank you.
I have a question. So should we be expecting like questions that don't meet these criteria and we're supposed to figure it out and like?
No. So on the quiz, I'm not going to get you to check the conditions at all. I'm going to say, assume the conditions are satisfied, right? But on an assignment, right, you have to check them. I'm not going to set you up. They're always going to pass. The thing is, in kind of real world situations, you do have to check it and it might not pass. And then you need to do more research. But that is, as they love to say, beyond the scope of this course. Then you need to call a friend, if that's the case. Right. But most of the time, right, if I have to have 10 successes and 10 failures, if my proportions are relatively close to 50-50, right, then I only need about 20, a sample size of 20 for each group, right? And then as my proportions get smaller and therefore the Q's get larger, right, or another shift in the other direction behaves the same way, right, then I need to increase my sample size. So it depends on what proportion you're trying to catch, right? But if it's close to 50-50, then you really only need a sample size of 20 and it's, you know, close enough. Or 30 is usually safe, right? So we don't need, you know, huge sample sizes, as long as the proportion is close to 50-50. Okay. Are you ready? We're ready for an example. I wonder if I can make this, can I do it on a white background? There, that's easier to read, I think. Many thanks to ChatGPT, but it's not very, I should ask it for a more elaborate situation, but I think this gets us started. Two water treatment plants, Plant A and Plant B, claim to meet the same safety standards. Yeah. So now, okay, fine, you meet the standards, right? But is one better than the other, potentially, right? And so an independent agency tests water samples from each plant to compare their performance. And so now, okay, fine, we can check if they meet the standards. That would be using a one sample proportion, right? The standard is some number that I want to compare it to, right? And then now we want to compare their performance. From plant A, 320 samples are tested and 290 meet the safety standards. Huh. And so now, when you're reading these questions, right, on quiz 4, you really only have 2 or 3 types of questions to choose from, right? One sample proportion, 2 sample proportions, or a chi-squared, which is for Thursday. But on the final exam, they'll all be mashed up, and you need to be able to read the question and figure out what type of question it is, right? And so when you see things like 290 out of 320, that tells me it's a proportion, right? This is going to be a proportion type of question. So knowing that, you have 1 sample proportion or 2 sample proportions, right? But because you have proportions from 2 groups, right, that's what tells me that I have a 2 sample proportion type of question. Okay? And so the first thing I want you to think about is the type of question. Now, of course, today we're talking about 2 sample proportions, and so it makes sense that they're 2 sample proportions. But I want you to reverse engineer it and kind of talk yourself into, okay, yeah, if I see something laid out like this, right, then it is a 2 sample proportion type of question. Okay. 2 sample proportions. That'll tell you what formulas to use, right? And it would tell you what conditions to check, and it tells you everything that you need to know, basically, right? And so an alternative way that this could be given, right, is 320 samples are tested, and whatever that proportion is, where's my trusty calculator? 290 divided by 320, that's my sample proportion, is 0.90625. So an alternative way that this could be worded would be 90% meet the safety standards. Then you need to calculate your successes, right? And so I think ChatGPT is kind of a one-trick pony, but I'll change the other one so that you can see the other way that it could be worded, right? Where I give you the proportion and you have to calculate the successes. From plant B, 300 samples are tested. Notice that we don't even need the same sample sizes. That's pretty cool, I think. And 255 meet the safety standards. So we'll be able to find some sample proportion that meet the safety standards for plant B as well. Part A, at a 5% significance level, is there evidence? Now, whenever you see is there evidence, that means you're going to do a hypothesis test, right? All the steps of the hypothesis test, right? And so it looks cute and innocent, but is there evidence tells me I need to do a hypothesis test of a difference between the proportions of water samples meeting safety standards at the two plants. There will be keywords, right, for determining if it's a proportion type of question, right? Usually, or I'm going to say always, the word proportion is going to be in the question somewhere, right? And so that's something people struggle with a lot. How do I know if it's a proportion question or, spoiler alert, a means question, right? Crazy, right? Where we analyze averages for numerical data, right? Well, usually it'll have the word proportion in there, right, somewhere. Yeah. And then part B, construct a 95% confidence interval for the difference between the true proportions of water samples meeting safety standards at plant A and plant B. Aha, okay. Nothing to it but to do it. Here we go. I'm going to check the conditions for this one. And then for the next one, I'm going to say assume the conditions for inference are satisfied. Right, kind of cheating, but I want you to see it in action and then we'll kind of parking lot it. Okay. I'll call it step 0. Check the conditions. We read the question, and I'm going to need to do a hypothesis test, but then it says construct a confidence interval, which means you have to do a confidence interval. That one should be pretty obvious, right? It'll always say construct a confidence interval, right? So for our conditions, we have to check both the confidence interval and the hypothesis testing conditions.
Right.
Yep.
Is that significance level? Is that the same as like alpha?
Yeah. Yeah. Nice.
Can you just use like the T-calc formula to ask cool stuff, do the same, and do two separately?
You can use the confidence interval for a hypothesis test. Is that what you mean? But then the S pooled and the T distribution are for numerical data, which we're not there yet. I mean, technically a proportion is an average. And so we could go from there, but it's nice because it follows the Z distribution. That's the only difference. Whereas T has degrees of freedom and kind of makes room in the tails for small sample sizes. Simpler conditions though for the T distribution. Z makes us work for it. Okay. Independence. There's no mention of these samples being randomly selected. That's okay. We assume they were randomly selected, right? And then we can assume that they're independent of each other. And so what we're going to say is we assume the samples were randomly selected. So I flip-flop between calling it check the conditions and slash state the assumptions. These are the assumptions that you're making heading into doing your test, right? And so in this case, right, we assume the samples were randomly selected. Okay, then we can move forward. That means that these 320 are all independent of each other, or at least we can assume they are. And these 300 are all independent of each other. But then we have that follow-up that plant A has to be independent from plant B. Right? And so we assume plant A is independent if I make it look like a mess, you can't read it anyways, of plant B. Fair enough? Huh? How about the normality condition? The normality, or if you prefer to call it the sample size condition, right? The reason we're able to assume it follows a normal distribution depends on if you're doing a hypothesis test or a confidence interval. Yeah. And so for a hypothesis test, that's part A. We need at least 10 expected successes in each group and at least 10 expected failures in each group. And so here, we need to calculate the pooled proportion. Right? Before we can go ahead. But then we'll have it. Right? Then we'll have that pooled proportion for our calculations later. So your pooled proportion is either x1 plus x2 over n1 plus n2, or you might have to calculate the number of successes from your sample size and your proportions. But in this case, we have our successes. Let's see what we're given here. And I guess I could call them NA and NB. Or I could be lazy and call them plant 1 and plant 2. Whatever. And A is 320. And the number of successes at plant A is 290. NB is 300. And XB is 255. So I have my successes in each group and I have my sample sizes in each group. And I'm just going to copy this so I can see it. Okay, not like that. I'll erase that, but let's see here. And A is 320 and B is 300. XA is 290 and XB was 255. And now I'll erase that. So my pooled proportion is I shove all these successes. And to keep it nice and tight, I am gonna painfully put my equal sign across the page. I know, I hate that. No, you know what? It's virtual paper. I'll stack my equal signs, do it properly. I don't know why ugh. So this, of course, is going to be XA and XB and NA and NB, right? Or XA plus XB over NA plus NB, if you want to be particular. 290 and 255 over 320 and 300. 290 and 255 makes 545 and over 620. I get a p hat of 0.879032251. Let's round this to 4 decimal places. Usually proportions are safe at 4 decimal places. Right? Ideally, keep all your decimal places, use the store function, but just for kind of ease of writing. .8790 or 0.879 if you want. Okay, now I can use this to find how many successes and failures I would expect if the proportion is 0.8790, right? They're all grouped together. So now we need at least 10 expected successes in each group. N1 times p hat. N1 was 320 times p hat 0.8790. $281.28. That's greater than or equal to 10. I'll do N1 times Q hat. I'll do my failures here. 320 times 1 minus 0.8790. 1 minus 0.8790 is 0.121 times 320. 38.72, which is still greater than or equal to 10, so that's great. Now I've checked my first sample. All right, then I need to do the same for my second sample. Okay. Notice how this p hat 0.8790, right, has a shift, right, which means that q hat, therefore q hat is 1 minus p hat, which is 0.121. Right, so they're quite off of 0.5, 0.5, right, a 50-50 split. And so then I need a larger sample size, right? And that's highlighted by, okay, I only expect 38.72 failures, right? Which is still large enough, right? So these aren't strict conditions, but we have to check them anyways. N2 times p hat is 300 times 0.8790. $263.7, which is of course greater than or equal to 10. It's my failures that I might be concerned about because this is a smaller sample size, right? 300. And so N2 times, whoops, Q hat, 300 times 0.121. 36.3, which is still greater than or equal to 10. I like to put a little check mark there. What's another thing you could have done? Instead of N2 Q hat, you could have said, well, 300 is my total. 263.7 are my successes, so the remainder must be my failures, right? They're equivalent, so it doesn't matter. Doesn't matter how you got there. this work was all kind of going to be useful in our test statistic as well, right? And so then we're just gonna grab it from here. But that was just for the hypothesis test. And so now we need to check it for the confidence interval. I need at least 10 observed successes and at least 10 observed failures in each group. Well, at least 10 observed successes and at least 10 observed failures in each group. In this case, we have the successes, and so we can calculate the failures. Right. So I have X1 or XA if you want. XA. I've been flip-flopping. That's okay. XA was 290. That's greater than or equal to 10. NA minus XA is 320 minus 290. It's 30, which is greater than or equal to 10. XB was 255, which is greater than or equal to 10. And NB minus XB is 300 minus 255. $45, which is greater than or equal to 10. For consistency. So it's nice when you have the number of successes, right, to check your conditions. Now we're ready for the meat and potatoes. Step one. Well, I guess I should say, therefore, the conditions for inference are satisfied. That means we can go ahead and actually answer the question. Okay. Part A. And maybe I'll copy past it here. I know we've been working for so long. Feels like we should have at least started the question, but we have not. As we mentioned, the 5% significance level means that alpha is 0.05. So I'll jot that down, which is also our default. And so we're going to do a hypothesis test. And so step one is state the hypotheses. Now, this is where so earlier, I fear I was jumping around back and forth between 1 and A and B and 2 and whatever, where I've assigned A to be group 1 and B to be group 2, of course. As long as you kind of say what you're going to let group 1, group 2 be, it's fine, which I didn't. So it's not fine, I guess. In your hypotheses, you have to use question-specific subscripts, Okay, because P1, P2 don't mean anything unless you attach to which group you're talking about. Okay. So our null hypothesis is that PA minus PB is equal to 0. I have to assume that these two groups are the same, these two proportions are the same until I have proof otherwise. Now, from the question, I find my sign for the alternative hypothesis. I want to know if there's a difference between the proportions, right? And so this tells me that I have a not equal to, right? I don't care if one is less than the other or the other one. Well, I guess that would be the same. PA minus PB is not equal to 0, right? They're significantly different from each other. Or if you prefer, you could say H naught is that PA is equal to PB. But because of that symmetry with the point estimate and minus the null value, I like this version, right? And I guess my question to you is, do you want both versions on the formula sheet or just one? Just one. And which one? This one. More proper. You're allowed to use this one if you want. Just pick one. Pick one that you like. They mean the same thing. In the textbook? I suspect she would introduce both, but then kind of stick to this one. Don't know for sure though. Yeah, two-tailed test. Right, so this here tells me that this is a two-tailed test, which means I'm going to parking lot that information until my p-value, but it means my p-value is the area in both tails, right? I find it in the one tail, and then I say, well, I would be just as concerned if I saw something as extreme on the other end, right? So I multiply it by 2. Okay. I will say here, no, you know what? It's going to be in red. We must use question-specific subscripts in the hypotheses. You don't want to make your reader kind of hunt around and figure out what group 1 is and group 2 is, right? Later on, you can say something, then you can say let group 1 or let plant A be group 1 and let plant B be group 2, right? But here you have to talk about A and B because otherwise you're sending me, the reader, all around town looking for how you define your group 1 and group 2. And usually I just do them in the order that they appear. Once you've done this, then you can do your just generic 1 and 2s. Step 2, do the test. We need our Z, which is going to be on your formula sheet. Z is P1 hat minus P2 hat. Technically minus 0, right? How far is it from this hypothesized difference of 0? But I don't write that, right? Because we're kind of, we've introduced that. We understand that it's there, kind of hanging out, but we don't need to write it because there's a lot going on anyways. Divided by the square root of P hat Q hat times 1 over N1 plus 1 over N2. I'll say recall that P hat was 0.8790 and Q hat was 0.1210. We already found those, right? From checking our conditions, we found the pooled proportion and thus the pooled failure proportion. But I still need my P1 hat and my P2 hat. Yeah. So let's do that on the sly here. And copy. PA hat, or P1 hat if you prefer, is going to be what? 290 over 320. $290 over 320. Is 0.90625. Or 0.9063 to 4 decimal places if you want. I don't really see any harm in keeping all those decimal places because it's just one more, but whatever. Which means Q1 hat is 1 minus 0.9063. Or I should say QA hat is 0.0937. Which I don't need here, but I will need it for my confidence interval. So you may as well just kind of lump them up. PB hat, 255 over 300. Ah, nice, beautiful 0.85. Therefore, QB hat is 0.15. One thing that you can do to check to make sure you're on the right track is that your pooled proportion should always be between these two. Right? Because what did we do? We said, okay, if 0.85 and 0.90625 are basically the same, then I should be able to represent them with 0.8790. Right? But we're about to determine if there is a significant difference between these two. There's a difference, right? They're not the same. But is there a significant difference once we take into account the spread that we're expecting to see from these sample sizes? Okay, so usually I would kind of tackle this at the beginning of the question, kind of where I highlight, you know, all the things that I'm given, I would tack on and calculate my p-hats right away. But I didn't give myself enough room, so I had to do it later. And we didn't need it until now. But now we're ready. P1 hat minus P2 hat, PA hat minus PB hat. So Z is going to be 0.9063 minus 0.85. How far is that observed difference in proportions from 0? Divided by the square root of 0.8790 times 0.1210, all times 1 over n1 or NA, which is 320, plus 1 over n2 or NB, which is 300. I would simplify 1 over 320 and then simplify 1 over 300 and then add them up and then multiply them through, right? And then don't forget your square root. Okay? Because otherwise your values are going to be just insane. And test it out. So we've got a difference of 0.9063 minus 0.85. 0.0563, pretty small. But is it close enough to 0? Let's see. I can't wait to find out. So if I do 1 over 1 over 320, and then plus 1 over 300, I get a very small number. Because I'm lazy, I'm not going to write it down. I get 6.458 times 10 to the negative 3, right? Once I do this. Then I'm going to multiply it by 0.121, and maybe I'll make this smaller. Times 0.121 times 0.879. I get something very itty bitty. The square root of 0.00068901875. 1, 2, 3, 4. Okay. Once I take the square root of that, though, I get something kind of reasonable looking. What would happen if you divided 0.0563 by this tiny, tiny, tiny number, right? You're taking something relatively small and splicing it up into many, 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 many pieces, you're going to get a huge Z, right? So whenever I get a question, I found a Z that's just huge. Did you forget to take your square root? Right? Sometimes it is going to be large, right? But often not. 0.026208812993. Now I've got some beef here. I shouldn't keep that many decimal places because I used rounded values, blah, 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 whatever. 0.0563 divided by that guy. I get a totally reasonable Z of 2.148132392. Okay. You could use the norm.s.dist, right? Use Excel or use your calculator to find the area in one of the tails, right? Which is going to be our third step. Find the p-value. .148. Right. I'll use a Z 2.148 to 3 decimal places. Kind of lose interest. There's nothing happening after 8. Z is centered on 0. I found a Z of 2.148. So my one-sided p-value is the area in the tail from 2.148, right? And above 2.148. But then if we want to know if there's a difference from 0, right, then I would be just as concerned if I saw this down here, a negative 2.148. And so that's why I take my one-sided p-value and I multiply by 2. Now, I would say norm dot s dot dist in Excel of 2.148, true. And I guess I should I'll just make it a little bit shorter, because that's going to, the norm dot s dot dist gives me the area to the left, but I want the area to the right. And so I can shorten this up 1 minus that. That gives me the area to the right. Now, you can use your calculator, or do I try to find my Excel? Fine. Try to not use oh, hey, one's ready to go here. Let's just change it. what was it? 148. .148. I get the area to the left is 0.984143. Can I do this? Equals 1 minus that guy. Hey, I'm getting better at this. But then I want to multiply it by 2. All right. And so here, I'm worried I'm going to fly too close to the sun here. It's going to be this times 2. Bink. Oh. Oh, that's old. Hopefully it's this one. Crop it up. .015857. And so this is going to be the one-sided p-value. But we have a two-sided test. And so the two-sided p-value is going to be 2 times the one-sided p-value. 0.031714. Small. Smaller than 5.
The normal CD on this will just give you the area inside area 2 that sort of.
Yeah, however you find the area is good by me, right? I'll use the Excel output on the front page, but if you prefer to use your calculator, that's totally fine, right? Yeah, I think your calculator needs an upper and a lower bound. And so then your lower bound would be, you could set it to be 2.148, and then your upper bound could be like 99 or something.
I just do the -2.
Oh yeah, between here.
Yeah.
And so take it away from 1.
Yeah.
Nice.
Do that right away.
Yeah. That works too. Yeah, however you want to do it, right? These are all just puzzle pieces. So as long as you know what it is that you're getting, then that's cool. Nice. Okay. Now our conclusion. What? I know, makes you want to quit. I'll do it on a fresh page here. Our conclusion. Our conclusion has 3 parts, right? You can compare your p-value to your alpha level, right? And in the question it said at a significance level of 5%, which tells you to use alpha of 0.05. So then you compare your p-value to your alpha level, and if it's less than the alpha level, if the p is low, then the null hypothesis must go. So you show off all the things that you know, right? You've done a lot of work, right? May as well put it in writing. Since our 2-sided p-value, right? Show off that you knew to find a 2-sided p-value of, show off that you know what it is, 0.031714. This is less than 0.05, right? And so is less than our alpha level of 0.05. Show off that you know what the alpha level is, right? And if I don't give you an alpha level, then you assume it's 0.05, right? And so you would still say what it is you're comparing it to. I don't enjoy reading things that say the p-value is less than the alpha level, so I reject H naught. Okay, yeah, but you got to support those statements, right? So you have to say what the p-value is, and you have to say what the alpha level is. Right? It is less than our alpha level of 0.05, which means we have enough evidence to reject H naught. Now that conclusion has to be in terms of the null hypothesis. You only have enough evidence to reject H naught, or you don't if it's greater than alpha, right? And those are your only 2 options. Why? Because we did all our hypothesis testing, assuming the null hypothesis was true, and then we found evidence against it, right? And so, right, your conclusion has to be in terms of H naught. If you're rejecting it, which we are in this case, then you can offer up the alternative, right? And so, which means we have enough evidence to reject H naught in favor of HA. And then the part, arguably the most important part of the question that students love to forget, because at this point you're tired. You've done a ton of work. But what does this mean in terms of plant A and plant B, right? That's where we started this whole thing, right? They're the troublemakers. So let's see here. If I have enough evidence to reject H naught in favor of HA, right? What does that mean? It means that there is evidence of a difference between the proportions of water samples meeting safety standards at the 2 plants, right? You take the question and you reword it as an answer, and then you're done. I'm going to copy this.
So which one is that? Did we learn anything from this?
No.
Good, okay, just checking.
And that's important too, because hypothesis testing doesn't tell us that. It just tells us that there's a difference. And that's why we need the follow-up of the confidence interval to attach some numerical value to that difference, right? So thank you for that beautiful segue. Couldn't have planned it better myself. So here, you reword the question as an answer. I'm not concerned about, does it sound wonky, right? I'm not concerned about anything like that. Just reword the question as an answer, right? If I wrote the question weird, that's on me, not on you. And so of course, if you're publishing or you're giving this to your boss or whatever, then yeah, spend some time on your conclusion, right? But for these, we're just starting. Therefore, there is evidence of a difference between the proportions of water samples meeting safety standards at the two plants. Period. And now I'll delete this. How much time do I have? 3 parts to your conclusion. Compare your p-value to your alpha level. Right. Then your conclusion in terms of the null hypothesis. Then your conclusion in terms of the question. I guess it was ambitious to have 2 examples. These always take a long time. I know they take a lot longer for me to talk about than for you to actually do, but still. Especially if we don't check the conditions. So now, construct a 95% confidence interval for the difference between the true proportions of water samples meeting safety standards at plant A and plant B. And so this, a confidence interval, tells us what the difference might be. Right, we found that there was a difference. Now what is it? Right, a reasonable follow-up. Okay. For 95% confidence interval, for a 95% confidence interval, use Z star is equal to 1.96. From here on out, I'll give it to you, right? We did practice and we know where that came from, okay? We have to move out 1.96 standard errors to capture the central 95% of the curve, but now we've outgrown that. Those were training wheels. So our confidence interval looks like this, and maybe I'll do not generic, PA hat minus PB hat plus minus Z star times the square root of PA hat QA hat divided by NA plus PB hat QB hat over NB. Tedious, yes, but hard, no. I'm gonna grab all the calculations that we did up here. Because time is breathing down my neck. I can feel it. Okay. Plug and chug at this point. Right? Just be careful with your bed mass, right? Figure out this first component, then the second component, then add them together, then take the square root, then times 1.96, right? Kind of nice and slow, but we get 0.9063, oops, minus 0.85. Notice that this is the same difference that we had in our test statistic, right? Because now we're just attaching to, okay, if that's my difference, then what's a reasonable range around that? Plus minus 1.96 times the square root of 0.9063 times 0.0937 divided by 320 plus 0.85, oh, this little cutie, times 0.15 over 300. I'm going to whiz through, or try to whiz through this. 0.9063 times 0.0937 divided by 320. I'm going to store that in A. 0.85 times 0.15 divided by 300 plus recall A. I'm trying. And then the square root. Don't forget the square root. You'll find that this is a similar standard error, right? 0.026275005654. But at that point, who cares? Times 1.96 plus minus 5% is basically what it's saying. 0.051499. Let's drop it there. 0.9063 minus 0.85. So we get a difference of essentially 5% plus minus 5%, right? Quite large bounds in my opinion. 0.0563. So my interval is 0.0563 minus 0.051499. You get something very, very small, 0.004801. 1, 2, 3, good. 0.0563 plus 0.051499 up to 0.107799. In terms of, is this off of 0? Yeah. Technically, but it's kind of close, right? And so that's what we found with our Z of 2.148 as well. Right? But now our job is to interpret this interval. And I'm sadly going to need another page. But I can draw this here. 0.004801 up to basically 10%, 0.107799. And a difference of 0 is on the outside, right? So that's evidence against the null hypothesis. Right? I'm 95% confident that 0 is not one of the options, right? And so then you could use that in your hypothesis test, but now we need to interpret the interval and we use the same blurb, right? We are 95% confident the interval from 0.004801 to 0.107799 captures, right? That's the same setup that we were using before, right? Captures, and then whatever we were asked to build a confidence interval for. Captures, copy. Fine. Captures the difference between the true proportions of water samples meeting safety standards at plant A and plant B. Now, because this is entirely positive, what does that mean about A versus B? A is consistently higher, right, than B. Okay. So notice, right, that these are positive. Therefore, A is consistently higher. I know, I'm on borrowed time. Than B. There. If you have any questions, let me know, but please enjoy this, this other example as well, which we didn't get to. I'll stop this.